Okay, so as I said, there's only a little bit left. The rest of this week, we are going to go through exponent laws 1, 2, 3, 4, and now 5, and tomorrow 6. All the exponent laws you will need, we will learn this week, so that you can handle anything that comes your way when we start using it as a graph. Right. So let's start with the exponent law number 3. I want to show you some special cases where I don't want you to be tricked. Would everyone please take a look at this sheet? Yes, and take a look at number 5. Number 5 being the power rule. Do you remember in class I said if you have some kind of base and that had, let's say, a 5 as an exponent, and that entire thing was the base to another exponent. And you want to remember the shortcut. What does the exponent law tell you about power of a power? Yeah. Good. This particular law applies to anything inside the bracket. So here's another example. Okay, if I give you something like 3a squared, so a 3a cubed to the power of 2. The final answer to this would be, anyone know? Let's do the exponent first. This would be a to the power of, correct? But 3 is actually to the, 3 becomes the 9. Let me try to explain. This is the same as saying 3a cubed multiplied by 3a cubed, which is the same as 3 times 3, a cubed times a cubed, 5, 6. An easier way we can do this is assume that the 3 has a power of 1. This 2 multiplies with both of these. Just be careful. Let me give you another example. Okay? If I have, how about this? 2 over 5 is all to the power of 3. Want to take a guess? No. This is 2 to the power of 5 times itself. But mathematicians, being lazy as usual, we don't want to write that. Isn't it easier to write 2 to the power of 3 over 5 to the power of 3? Right? 2 times 2 times 2, 5 times 5 times 5. The final answer is 8 over 125. I can do that for you, and you can do that in the calculator too. But is there a way we can create a shortcut for yourself to go from here to here? What can you tell yourself? What is something you can say to just go from here to here without writing that, to save yourself time? Because that's the whole point of exponent laws. Okay? Not add, because remember, it's 2 to the power of 1 and 5 to the power of 1. You're not really adding. What are you doing instead? Not quite. Sure. 1 times 3, then 1 times 3, then. Let me give you another example. Ready? X to the power of 2 over y to the power of 3 divide all to the power of 4. You're not adding 2 plus 4. What does this equal to? What does that equal to? It is 2 times 4 and 3 times 4. So it's x to the power of 8 and y to the power of 12. Here's my shortcut. And again, if you want an explanation of why that shortcut works, x to the power of 2, y to the power of 3, x to the power of 2, y to the power of 3, x to the power of 2, y to the power of 3, x to the power of 2, y to the power of 3. How many x to the power of 2s am I multiplying? 4 of them. So using exponent laws, this is actually 2 plus 2 plus 2 plus 2, which is the same as 2 times 4. And over, it's y to the power of 3 plus 3 plus 3 plus 3, which is the same as 3 times 4. That's why the shortcut works. Okay. Any questions?
I just logged in. Did we cover the expanded power rule?
Nope, that's essentially what I'm doing here.
Okay. I'm confused because there's a rule here that's examples.
So yeah, so expanded power rule is just basically a tricky version of the power rule, power of powers. And the idea is this. Cameron, just for the sake of it, give me an example with an obscure term here. Just give me the most complex term you know. 1 over 27. Give me some letters. Q. More. W. Give me some exponents on there too.
5.
Okay, 5. 7. Give me some more letters. H. Okay. J. B. And then another exponent. 7 and one more.
9.
Okay, so J to the power of 9. Okay, and then one not so big letter, not so big number. 2. Okay, so let's say that was my test question. And I say simplify. The power rule suggests that this, whatever is here, is just multiplying, right? It's just, we're multiplying this base twice. But instead of writing this out, instead of doing 1Q5HB7 over 27W7J9 times 1Q5, lazy. This thing simplifies too. And this exponent will multiply to every exponent inside the bracket, just as we've always been doing. Remember, if you have, let's say, x to the power of 2 to the power of 3, the 3 multiplies to the exponent of 2. Well, that applies to everything in here. So 1 has a power of 1, Q has a power of 5, H has a power of 1, B has a power of 7, 27 has a power of 1, W has a power of 7, J has a power of 9. Let me write that a little more clearly so that you are not confused. All of this to the power of 2 is 1 times to the power of 1, right? 1 times 1, it's 1 to the power of 2, which doesn't change the number. 5 times 2, it's q to the power of 10. 1 times 2, h to the power of 2. 7 times 2, b to the power of 14. 1 times 2, 27 to the power of 2. 7 times 2, w to the power of 14. 9 times 2, j to the power of 18. Please take a look at all the exponents on the left side and all the exponents on the right side. You will see that it has doubled. This is what I mean by the expanded or the extension of the power rule. It's not supposed to be rocket science. It's not supposed to confuse you. But you need to know that if you were to do the power of power properly, this is exactly what happens. And so there's your shortcut. Yes. It would be 1 to the power of 2, but I mean, 1 times 1, it becomes a 1, so I decided not to write it. But if you wanted to remind yourself that is in fact what is happening, absolutely, you can put that there. And yes, you can simplify that. 1 times 1 is 1, and 27 times 27 is a very large number. You can solve that if you wanted to. Okay. All right. Today's lesson is very short. I'm basically going to show you number 6, and that is law number 5. It's labeled number 6 here, but law number 5, negative exponents. Why am I doing this? Let's put it this way. If I had a graph and my equation was, as I said, this is our goal, right? Let's pretend my equation was 2 to the power of x, and I want to graph it. I want to know, what is the value of y when x equals a 0, when x equals a 1, when x equals a 2? And I would plug it in, plug it in, plug it in. And I start drawing points on this direction. But does that mean there's no points on the left side of this graph? Of course there is. But what's the x value on the left side? Is it positive or is it negative? It's positive or negative. It's on the left side. These are going to be negative x values. So we also need to know how to plug in negative numbers into an exponent. And that's today's rule. Consider this, everyone. Here are some examples I'm going to write out for you, and you tell me what's happening. Ready? No, let's do something easier. 3 to the power of 4 would be 3, 9, 27, 81. Okay. Oh. Last example. All right. This one might be a little tricky. But looking at the first 5 examples, what happens if you have a negative exponent? I'll give you a minute. Formulate your thoughts. Take a good guess. So if you need a way to organize your ice, so it's left side versus right side. I'd like you to consider the difference between the left side and right side. By placement, what do you mean? So if you're to give a definition to yourself, every time you have a negative exponent, what do? You are writing the reciprocal, you are flipping. The numerator and the denominator gets flipped. It's literally this. What I mean by that, just to prove a point, 2 to the power of 1 is sort of like 2 over 1, right? To the power of 2. So 2 is the same as 2 over 1. If you have a negative exponent, the entire base gets flipped. The 2 goes down to the denominator, the 1 comes up to the numerator. If it's 3 over 5, well, it's just 3 over 5. But if it's 3 over 5 to the negative 1, it's actually the reciprocal. So anytime you see a negative exponent, you're bringing the numerator to the denominator and vice versa. The same with the last example. Take a look. 1 over 3 squared is just the normal question. It's 1 over 9. But look at this. 3 to the power of negative 2. 1 over 3 to the power of negative 2 is the same as bringing that on top. If you have a negative exponent, just change its location. That's the best shortcut I can give you. And there's a very good reason for it, and it requires simple division of fractions. But I'm not going to go in there because I feel like it might distract you or just confuse you even more. Since we're talking about shortcuts anyways, anytime you see a negative, change its location. Here are some examples. I'm going to take out my the sheet that I just gave you. I don't think I have it open yet, so give me a second. But please take a look at, we will start with, if you turn the page, the exponent practice. The front page is all about different examples where the answers are given to you. The back page shows you a bunch of practice questions we can try. So I believe the negative exponents begin from question 19 on. So let's practice it together. I'm going to zoom in a little bit. And we will do it like so. New share. Here we go. So in the sheet, I can't zoom in any further. Give me a second. Let me download this. Okay, here we go. Is everyone with me? Please turn to question 19. We're going to do as many of these as we can in the next 10 minutes, and then I'll give you a bit of a break. Everyone with me? You've turned the page? We're starting with 19. Step 1. Ooh, you see a negative exponent. First thing you do, remember, this base is y over 1, right? Don't be fooled. It is a y that has a denominator of 1. So you have a negative exponent. What happens? It's the key word of the day. It starts with F. Yes. Okay. Becomes 1 over 9, all to the positive 7. And if you want to simplify that, using the expanded power, isn't it 1 times 1 times 1? Isn't it 1 to the power of 7? And y to the power of 7? But of course, what's 1 to the power of 7? 1. So there it is. Next, Remember, this 7 is actually 7 over 1. Oh, there's a negative exponent. What do you do? Yep, 1 over 7, all to the positive 2. And if I simplify it, 1 times 1 is a 1. 7 times 7 is 49. Oh no, I have a negative exponent in the denominator. What happens to that base? Where does it go? Hint, it's in the denominator right now. No. The hint is denominator. What is the other ominator? Huh? Numerator. This becomes x to the power of 5 over 1. This becomes a positive. We do not want to leave any answers as a negative exponent. How about this one? Following the trend, 2 to the power of negative 4 is in the denominator. Your thoughts? Yep, 2 to the power of 4 over 1, and 2 to the power of 4, 2, 4, 8. You can solve that as 16. '23, I think you can do it. We've done it before, so it's a bit of a switch up. Before you actually solve the negative exponent, how about we just use the multiplication power rule, exponent law? What happens to the exponents when we're multiplying the same base? Yes. 5 plus a negative 1 is 5 plus the negative 1. It's like I'm basically a subtraction. This is x to the power of 4. All right, that's a good switch up. Number 24, x to the power of negative 6. Oh, we don't like the negatives as the final answer. How do we deal with it? Yes. Yeah, that's x to the power of 6. I could have written it like this, where the entire base is to the power of 6, and then simplify it as 1 over x to the power of 6 if you want to. But sooner or later, you're going to get sick of writing that middle step. And so feel free to skip it. All right, so we're getting the hang of it. What about this one? Number 26. The same base are multiplying with each other. Yes. Yes, so what happens to the exponent? It's negative 13 plus 4 plus 6. What's the final answer? Negative 13, add a 4 to it, add a 6 to it. It's like negative 13, add a 10 to it. Yep. Correct. And I would leave it like that, but we don't want negative exponent as my final answer. So, and it becomes, yes, that's my final answer. Once again, this is the exponent law number 1. What happens when you're multiplying the same base? The exponents will add. So negative 13 is added with 4, it's added with 6, that's a negative 3. The exponent is negative 3. Let's keep going. Here are some more complicated questions. Let's see what the next column has in store for us. Yeah, number 27. How about it? What happens when we're dividing? What happens to the exponents? Yes, negative 1 is being subtracted by a negative 8. So that's sort of like saying negative 1 is being added to an 8. So what's the final answer? It's the power of 7. Luckily, there's no negative exponent, so we don't have to work with it. But let's pretend you're so fixated on negative exponents that you want to turn it into positive exponents. What would that be? X to the power of -8, where does that go? Good, Jessica. This is x to the power of 8. And then what about x to the power of -1 here? Where does that go? X to the power of 1. What is 8 minus 1? 7. You get the same answer, people. So we know we're doing it right. We can go at one direction, other direction. We meet at the same place anyways. So you can do whatever you want, whatever is comfortable. How about this next one? Actually, would this one be better? No, number 32. Number 32. Take a look at number 32. Ooh. Don't be fooled, everyone. 3 is going to be working with the 12. The x, base of x, is going to work with the base of x to simplify. And then the y is going to work with the other y to simplify. So 3 divided by 12. Yep. 0.25. Let's leave it as a fraction. I'm going to divide both by 3, leaving me with 1 and a 4. This is 1 over 4. Can someone work out that exponent there? X to the power of 2 is divided by x to the power of 6. What is that? X to the power. So it'd be x to the power of -4. Don't worry about that negative right now. Let's just write it down. It happens. We'll deal with it later. Next, y to the power of -3 is being divided by y to the power of 3. Yep. Correct. So let's write this down. But this would be correct, but I want to be more correct by using mathematical conventions. We don't want negative exponents as my final answer. What is that equal to? Where does the x go? X is right now, it's a whole number. It's like that. Yep. 1 over x to the power of 4. And the y? 1 over y to the power of 6. And if I put that together, sorry for running out of space, it's 1 over 4 x to the power of 4, y to the power of 6. So again, the question is, do you want to deal with something as complex as that, or would you rather have it simplified? That's why we're learning all this. Question? Why did not? Oh, no, different base.
No.
Right? Oh yeah, it's not 3 because the 3 is actually already simplified. We divided both, so the 12 is gone too. So 3 over 12, we reduced it to 1 over 4. Yep. Yeah. Everyone, that's basically it. This is just practice to make sure you know how to work with negative exponents. Like even here, number 33, let's use that as my last question. Take a look at 33. How would you do it? And in fact, there's more than one way you can do this. How would you like to do it? Brendan, you want to give it a shot? Like if you saw this on a quiz or a test, what would you try to simplify first? There's 6 different exponent laws to choose from. You don't have to do one law always first.
I would simplify side of the bracket.
Get rid of this first, for example? Because what would that become?
That would become 1 over y to the power of 3.
Correct. And then what's on top? These 2. They haven't changed. So this is 2 x cubed, so that's 2x cubed, and y to the power of -3 became y to the power of 3. Now let's work that -2 out. What does a negative make you do? Word of the day. So this becomes y to the power of 3, 2 to the power of 2 times x to the power of 3. And we can simplify a positive 2. It's a power of a power. What happens to the exponents on the inside? This is y to the power of 6, 2 squared, 4, and x to the power of 6. That's my final answer. You don't have to do the inside first, but if you do, well, here's your answer. Let's say you did it the other way. You're like, I don't like this bracket. I'm going to work out the power of a power first. So this becomes 2 to the power of -2, x to the power of -6, and y to the power of +6. Do you see where that came from? And not everyone might see it. Hayden, do you see how the exponents changed? Do you know why that happened? Were you able to follow? Perfect. For those of you who didn't, remember, if you have an exponent, it multiplies to all the exponents inside. And now that I have this, all that's left is to deal with the negative exponents. 2 to the power of -2 is denominator 2 to the power of 2. X to the power of -6 is 6, which is the same as what we had on the other side. You can do it in so many different ways as long as you are true to the laws. They are interchangeable, the order, I mean. I hope that you'll use some time today to go through all the practice questions. I've mixed in these practice questions, some zero exponents as well. I hope you will get a chance to practice them. Thursday and a little bit on Friday is going to be my last lesson on exponents. Okay, I am going to give you a pretty good, straightforward, not confusing lesson on radical, like fraction exponents and what you're going to do if you get something like that in the future. And then we do our quiz. So think of this as it's one of the last hurdles. Okay, and practice and practice and practice. I promise you, the quiz that you see on Friday is essentially your homework check. Okay, definitely do this, and it's in your best interest to do well because it's not difficult. But if you don't practice the homework, it'll be the hardest. Right? It's stuff like this. Get it done. Any questions? All right.